Today we're finishing up Unit 6 with Lessons 17 and 18, Interpreting Rates and Which One Changes Faster. I want you to turn in your workbook to page 293. Complete the bridge, read carefully, and answer each question. Try to do this on your own before you come back and start the video to compare answers. Alright, you're asked to express each percent change using an expression that only uses multiplication. Remember, with growth or decay exponential functions, we use a formula that shows multiplication. Let me write that down. And you write this down in your workbook as well. Alright, so I'm going to use function notation. F of x, you can call this y if you'd like, but on the left hand side is our output of whatever we're measuring. So that's equal to a times b raised to the x. Sometimes I use a t. You can use other variables, but our input, our f of x, you could also call this y right here. Our output is equal to a is our initial amount, what we start with before we start measuring. B is our growth or decay factor. It's going to be growth if it's a number greater than 1. It's going to be show decay if it's a number less than 1. Growth increases and goes up. Decay starts high and then drops down. Now we're going to express each percent change using an expression that only uses multiplication. So it's going to be in this form. So we have x increased by 5%. X increased by 5%. Okay, that expression, in case you're confused, we still have some people that are turning in their cooldowns that are asking questions, so that's good, asking questions. All right, here's our 5%. This is 5 over 100. You can reduce that fraction to 1 over 20. Or you can divide 5 by 100, you get 1.05, or you can just put the 5 in the 100s place. All right, now we need to add that 5%, 1 plus 5%, and this is how we get 1.05. All right, now we have a decrease. So what do we do with that 10%? Instead of adding it, increase is add, decrease is subtract. We're going to take 1 minus 0.1. Remember, percent is over 100, so this is 10 over 100. That reduces to, if we divide top and bottom by 10, to 1/10. You can write 1/10 as a decimal this way. So what is 1 minus 1/10? It's going to be 9/10. Okay? So we're using the variable they gave us. Y decreased by 9/10. It's going to be y times 1 minus 1/10, which is 9/10 times y. Pay close attention to how they're asking the question, because a lot of times you're answering the questions, but you're not really looking deep at to what the question is asking, so you're getting it wrong. Following this model, we're going to increase. So we're going to be adding 25% to 1 and multiplying by x. Now I think they got the wrong answer here. Should be an x here instead of a z. Sometimes the workbook does that, so don't let that throw you off. Okay, x increased by 25%. So we start with an amount, initial amount we're going to call x. We're going to multiply it times 1 plus 25%. Okay, and then the last one, W, decreased by 2.5%. So this one's a little bit tricky. Okay, they didn't write it like the others. So let me just write it like 2.5 over 100. We're going to move that decimal 2 places because 100 has 2 zeros in it. What we're doing is we're dividing by 100. That's going to move the decimal 2 places to the left. 1, 2, and it's going to end up here. Fill in your missing numbers with 0. So that's 0.025, and we're going to subtract that from 1. Use your calculator. What is left over? Okay, 1 minus 0.25, they're saying is 0.975. Check with your calculator or Desmos. See if that's what you get. All right, hopefully you are checking. And if you subtract 25 thousandths, that's what this is, tenths, hundredths, thousandths from 1, you get 975 thousandths. All right, so work through these carefully. Don't rush through your problems on test day especially. All right, we have the population in a small town. We're going to start this warm up. So turn to page 293, read the problem. The population in a small town can be represented by the function P of t equals 3,800 times 1.052, which is 1 and 52 thousandths, to the t power, where t is the number of years since 2000. This exponent is always going to be your x-axis. Your x-axis is always time. Okay, the number of years since 2000. So 0 is going to be year 2000, and then this is 2001, 2002, 2003, and so forth. We start here and we're going up. It's really small and hard for me to read. Let me move it over a little bit. All right, this is 4,000, so this is 1,000, 2,000. It's going up by 1,000 each time. And that is representing our population. So what is the percent increase each year? Okay, the percent increase is 5.2%. Okay, so how do we do that? The growth factor is 1.052, which is 100, move that decimal 2 places to the right, 105.2%. If 100 is the current population, then 5.2 is the percent of increase. Now I can't look at the graph. Sometimes they have a graph as reference to see exactly what my starting point is, but in the equation, my starting value is 3,800. Does that look like it makes sense? Is 3,800 between 1,000, 2,000, 3,000? I would think it would be closer to 4,000, but this is just a sketch. Use your formula, your function, or your equation, whatever you want to call it, to find that initial amount, that A value. So it starts at 3,800, and we're going to multiply by 1.052. I'm not finding that by doing any math here. I'm just taking this, and I know this number is bigger than 1, so subtract 1 from this, and that's going to give us the percent of increase. Okay, so 1 plus our percent of increase is our growth factor, 1.052. Now we're going to use the graph to find when the population was 7,000. So they're going to tell you when to use the graph. So let's look at the graph. Now we're not going to go on the bottom because the bottom is always measuring time. The y-axis is measuring years, so I'm going to go up to 7,000. Start at 0, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. I don't think I'm counting right. We're counting by 500s. It's really hard for me to see, so make sure you're looking in your book. I think 7,000 is right here. Okay, and then go across, and then I'm going to hit the line right here, and I'm going to go down and find the number of years. And I'm reading that as 12 years after the year 2000, so that should be 2012. In 2012, the population was 7,000 people. Now let's turn to page 294 and complete activity 1. Read through the problem, read it carefully, highlight important information, cross out anything that is not important, and then focus on answering the questions completely and as precisely as you can, using the vocabulary and the formulas that we've used in this unit. Iodine 131 is used to treat thyroid cancer. A typical amount is used in therapy, and it's 150 millicuries. A millicurie is a unit used to measure radioactive materials. Iodine 131 decays at a rate of 8.3% each day. Now, I'm familiar with this because I have thyroid problems, and my sister has had thyroid cancer. And so treating your thyroid with radioactive materials is something that I didn't know about until she went through her diagnosis and was treated with radioactive iodine. So that's iodine 131. And you couldn't be around her while she was being treated with this. I want you to write a function rule in the form of f of x. So we're writing in function notation. Remember, you can replace this with y. F of x equals a times b to the x. So a is the initial amount, b is our growth factor. We're raising it to the power of x, and x is always time. X is going to be on that bottom axis. The y is the output, the y-axis. Now we're going to represent the amount of iodine 131 in millicuries as a function of the number of weeks. All right, so how much do we start out with? Look at this amount on the y-axis. Start with your function notation f of x equals, you start out with 150. Make sure you're looking in your book. It's hard to see on the slide. There's 140, there's 160, this is 150. And we're multiplying it by, now look at the rate of decay. That's 8.3. So take 8.3, 8.3%. We've got to put 8.3 over 100. That means we're dividing by 100. That would move this decimal 2 places to the left. Fill in this empty space with a 0. Okay, so it is decaying. We're going to subtract that from 1. So 1 minus 0.83 gives us 0.917. Make sure you're checking, using your calculator, and working through slowly and carefully. Now we're going to raise this to the power of x. We don't know what x is yet. We haven't told you a value to interpret this graph or this function for x. We've just set up the equation. So go ahead and put that in your graphing calculator. We're using Desmos, so put that in Desmos, and you should get a graph that looks like this. That's step number 2. Make sure you're stopping the video and graphing it, and then comparing, making the adjustments with that wrench in the upper right-hand corner to make sure that you have the correct graph so that we can use that to answer the following questions. After how many days will there be 100 millicuries of iodine 131? So we're looking for 100. You can start here and you can slide down until you see your y value change to 100. And that's going to be after about 4.7 days. It's going to be somewhere in here as you slide down. Question B says, how many days does it take for there to be half of the original amount of iodine? So we've got to look up here. The original amount is 150. 1/2 of 150, 150 divided by 2 is 75. So we're looking for 75 to be the output. So we're going to start up here. We're going to slide down until we see our y value change to be half of the original amount, 75, and that's going to be about 8 days. So it's going to be up here. When will there be less than 10 millicuries of iodine 131? So if you're reading your graph, that's going to be after 31¼ days, so somewhere down here. And you can look at the output on the left-hand side and you can kind of go to that area because we know that 10 millicuries is going to be around here somewhere. Practice with that. Don't go through this too quickly. Make sure that you're understanding how to answer these questions. You'll have some like this on the test. They're not hard to answer, but you need to practice doing your assignments, during your cool downs, doing your warm-ups, asking questions, and then the test will be a lot easier for you. Let's turn to page 295. We're going to complete activity 2. What is the rate? Now I'm going to give you a set of cards. If you're just watching this video, you're going to have to kind of work through it without the cards. But in class, I'm going to give you a set of cards, and you'll have, I think, 6 cards, and I'm going to give you those cards in pairs, and each person, you and your shoulder partner, should select a card and determine whether the given function has a growth factor or a decay factor, and then talk about and interpret what the growth or decay factor means in the situation of the problem that you're given. Then take turns with your partner sharing your responses, talking through it. As your partner shares, listen carefully, don't interrupt them. If you disagree, jot things down, discuss your thinking, and work to reach an agreement. Place the cards in 2 separate columns, one for growth, one for decay, and then choose another card. All right, so make a place on your desk for growth, make a place for decay, and then sort them into those 2 piles. When you're finished, arrange the columns for growth in order from situations involving the smallest amount of change or the least percent to the greatest, and then arrange the column for decay in order from situations involving the least percent of change to the greatest. You may want to pause the video before we move forward. All right, here are your cards. If you're watching at home, you're going to have 6 cards. If you're in class, I'll pass these out and then put these in piles, growth and decay, and then sort them in order. Pause the video and do that now. Do that with your partner. Here are the answers. Growth is going to be card 1. We have a growth factor of 1.32. That means we're adding 32% each period of time. That means the amount of bacteria increases by 32% for each quarter hour. Card 2, the growth factor is 2, and that means that the number of insects increases by a rate of 100% each week. Different ways we're expressing this. Okay? Think about that for a minute. If we have 100%, we have 1. If we have 2, we're multiplying by 2 each time. So we're increasing by 100% each week. We're doubling. Card 6, the growth factor is 1.06, and it means that the population increases by 6%. Move that decimal 2 places to the right. After you subtract that 1, that's going to be 6% increase each year. Now the decay factor on card 3 is 0.5. This is less than 1. And it means the amount of money won decreases by a rate of 50%. You could also say 1/2, with each place that we move. Card 4, the decay factor is 77%, or 77 hundredths. And it means that the amount of medicine decreases by 23%. So you would take 1 minus 0.77. Okay, and that's going to be how much it decreases every hour. 77%, when we're talking about decay, is how much remains after every half hour. So our time increment here is in half hours. And then card 5, the decay factor is 85% or 85 hundredths, however you want to read that. So that's how much is remaining. If you're asked what the decay factor is, this is what you'll give as the decay factor. If you're asked how much we're taking away, we've got to subtract that from 1. 15% is how much we're decreasing by each year. So we're going to take these cards, these decay, and let's look at the decay factor. 0.5, that's the smallest, 0.77, and 0.85. Putting them in order from least to greatest. Activity 2, what is the rate? You're given a function rule, f of x equals 1500 times 1 and 21 hundredths raised to the x power. Remember, x, whatever this number here, is always going to be our time increment. It's going to go along the x-axis when we graph it. This represents the amount of money owed on a credit card as a function of the number of years. So it looks like we're adding on 21% each year. Does the function have a growth or a decay factor? And explain how you know. So we're going to look at this b value. Is that number greater than 1? And the answer is yes. That indicates growth. If this was less than 1, that would indicate decay. What does 1.21 mean in this situation? What that means is we start with the initial amount of 1500. Each year, if we multiply by 1, we keep that original amount. Okay? But we're increasing by 21% by adding on that 0.21. So this is how much we would borrow. Then after 1 year, if we didn't pay anything at all, we would owe that initial amount plus another 21%. Then on year 2, we would replace that x with a 2, year 3, so forth. We would just replace that x with the exponential increments. Now go in your book through the lesson debrief. In general, make sure that you know how to graph an exponential equation and know how it helps you to solve problems. How can you determine if the factor is growth or decay? Look at the examples that have been given throughout this unit. If you have not highlighted in the lesson debrief, the summary or glossary portion of each unit, go back and do that before you take your unit test, which is coming up on Wednesday. How do you interpret a growth factor of 1.82 as a rate? Now the rate of increase is 1.82. Okay. Now the growth rate, how much we're going to add on each time, is 82%. How do you interpret a decay factor of 57% as a rate? We're going to subtract that from 1. Again, especially with decay, go through the summary glossary and focus on the examples. Look at the graphs. The more you go over this, the more familiar and ready you'll be for your test on Wednesday. All right, look at the examples of the functions, the way it's written. Initial amount is always going to be this first number that we start with. The number that's being raised to a power, and this x is going to be time, that's going to be either growth or decay. The growth factor it shows you here is 1 and 45 thousandths, which is 104.5%. Anything over 100% is going to show growth. Or if you change percent to a number, anything over 1 is going to be growth. The account balance increases by a rate of 4.5%. So it's going to be this right here is going to be what it increases by. Now we have another function. Our initial amount is 246. Now this number is less than 1, so this is going to represent decay. So the deer population is going to be decreasing each year. The decay factor is 86% or 86 hundredths. 100% minus 14%, 14% is what we're taking away, gives us that decay factor. The deer population decreases by 14% each year. The decay is the harder one for me to understand, so I want you to go over all of that carefully before the test. The more you go over it, the better prepared you'll be. All right, in Canvas, complete the cool down interpreting rates. For each function rule, identify the percent increase or percent decrease. Our initial amount, remember this is the A value, 135 is the initial amount. This number is bigger than 1, so this is going to show increase. What is the percent of increase? Is it 1.29 or is it 29%? It's going to be what we added to 1. It's going to be 29% or 0.29. In this one, we have a number that's less than 1, so this is going to show decrease. Okay, we need to take this number, subtract it from 1, and it tells us how much we're decreasing each year. All right, so for increase, if this number is greater than 1, we subtract 1 from this amount to show how much we're increasing. If this number is less than 1, we subtract this number from 1. Let me write that down. Okay, if we have a number greater than 1, subtract 1 to show the percent of increase. If we have a number that is less than 1, we're going to take 1 and we're going to subtract this number from 1 to show us what's left. That's the percent of decrease. All right, turn to page 301, complete the bridge. So pause now and then come back when you're done with the bridge. All right, for this question, you're a representative for a cell phone company, and it's your job to promote different texting plans. Okay, so we have functions A and function B. So highlight what you need to in that word problem. Okay, A and B, here's A and here's B, gives us the cost of each plan, where T is the number of text messages that we send. Okay, so this is a number of text messages. A little bit different than time. It's going to be the number of messages. Which is a better deal for someone who usually sends around 100 texts per month? So how would we do this? Okay, T is the number of texts. So in your calculator, replace T with 100. Okay, you don't need to put the whole thing, just put this. $29.95 plus 0.10, that's 10 cents, times 100. And then on the next line in your calculator, you're going to write this expression, 49.94 times 0.05 times 100. Which one is going to give you the best deal? It's going to be plan A. All right, so you can see I've put these two functions or equations into Desmos. The first one we started at $29.95, 10 cents per text messages. So with that, when I replace that T with 100, that would cost me $39.95 for the first plan, plan A. For plan B, it's going to cost me $49.94 per month, 5 cents per text messages. So that would be $54.94. Now I'm going to ask you to look at that and answer this question. Do you think this plan is best for everyone? Explain your reasoning. So there's no right or wrong here. This is just a chance for you to put an initial response. If you say, yes, I think that plan's better for everyone, maybe we didn't go high enough. What if we have 1,000 text messages, or 500, or even 200? The answer would be no, because if you send a lot of text, Plan B becomes the better deal, because the cost per text is going to be less the higher amount that you go up. So you can use your calculator. Let's just go back here and replace this with 500. Look here, the first one, Plan A, is cheaper. But if we experiment a little bit, let's put in 1,500 text messages. Okay, now Plan B is going to cost less. So for people that text a lot, maybe for work, it's going to be cheaper to go with Plan B. All right, so again, it's not just about getting an answer, it's about thinking things through and using your graphing calculator. So warm up. Graph of which function? Which equation do you think the graph represents? Equation A or equation B? Use this picture of this graph. What do you know about the graph? First of all, is it a linear graph? Does it form a line? Or is it exponential growth, where it starts and then it goes up? Or it starts and it goes down to show decay? This first equation, y equal 120 plus 3.7 times x, the initial amount is 120 here. If you look at B, the initial amount is also 120. But for equation A, it's a linear equation because we're adding y equals mx, the slope or rate of change would be 3.7, mx plus b, and the intercept is 120. Okay, so the only one that it could be is A, because it appears to be a linear equation, not an exponential curve. Multiplication by this growth factor, or this b, is going to show exponential growth because this is larger than 1, so it's not curving upward. Question number 2, what information might help you decide more easily whether the graph represents a linear or an exponential function? Did you think about how to answer that? Make sure that you're answering in complete sentences that make sense. Okay, one thing that I put is having a larger graphing window, adjusting with that wrench in Desmos. Some of you are still asking, you're saying you can't see your graph. You have to look at what your domain would be and your range would be and play around with adjusting that graph so that you can see it. So making a larger graphing window or putting in more points might show us something different. Let's go to activity 1, simple and compound interest. Turn to page 302. I'm going to read this once, and then I want you to go back in your book and read it again. The first time I read it, it's just to get a general understanding. So listen and just do nothing but listen. A family has $1,000 to invest and is considering 2 options: investing in government bonds that offer 2% simple interest, or investing in a savings account at a bank which charges a $20 fee to open an account and it pays 2% compound interest. Both options pay interest annually. Now here are the 2 tables showing what they would earn in the first couple of years if they do not invest additional amounts or withdraw any money. So you have the bonds. Okay, that's the first option. Okay, this is what they're going to earn each year. Start with 1,000. After year 1, it goes up to 1,020, and then year 2, 1,040. In the savings account, okay, we're going to start with 1,000, but they charge a $20 fee to open it, so that's why we get $980, because they're going to take that $20 for help in opening up this account. and they pay a 2% compound interest. So after the first year, they're going to have $999.60. Compare those two. And then after the second year, they're going to have $1,019.59. Now, what are the quantities in this situation? A quantity is something that can be counted or measured. Okay, so I want you to do a second read, pause the video, and highlight important information. All right, now that you've come back, had a chance to think about what we're looking at. Okay, we have bonds. Okay, that's going to be this one. 2% simple interest. So it's going to go up 2% each year. So remember, we start with 1. 1 means we're going to have that whole amount plus 2%. Remember how to write percent. Move that decimal 2 places to the left. So it's 1 plus 0.02. Okay, that's what we're going to multiply by the initial amount. So you can write that out as you remember what the equation for growth is. Okay, highlight anything else. For that second one, we've got a $20 fee. Okay, look at the quantities. Keep going. I'm not going to give you everything. All right, now describe the way the investment in bonds grows with simple interest. Try to answer this on your own after you've highlighted the question, looking at the graph. All right, the bonds grows linearly. If you put that in Desmos, it increases by $20 every year. So this is going to be our slope or our rate of change. However you say that. For the savings account, we have the amounts $999.60, and then we have $1,019.59. 999.60 is 1.02 times 980. So we're not just adding each year, we're multiplying by the initial amount times 2%, or 2 over 100. Okay, and $1,019.59, we get that by multiplying the initial amount by 1.02. Okay, just each time we go up, we multiply by 1.02. So it's showing growth. For each option, write an equation to represent the relationship between the amount of money and the number of years of investment. So we've already kind of talked about this a little bit. The first one is linear. So we start with the initial amount, and then our increase is $20 each year, so 20x. Y equal mx, the rate of increase or the slope is 20, plus b, the initial amount. For the second equation, our initial amount is not 1,000 because we had to subtract that $20 to begin with, but our rate of change is 1.02. We have that initial amount plus another 2% each year. Okay, and then we raise that to the x power. X is the years since investments were made. B is the value of the bonds, and S is the value of the savings account. B is for bonds, S is for savings. So I chose variables that help me remember. Now put these in your calculator. Which investment option should the family choose? Use your equations or your calculations to support your answer. So just coming up with an answer is not enough. You have to explain. Now the responses can vary based on what you're looking at, but you really need to practice putting this in your calculator and practice answering. All right, the government bond increases at a faster rate for the first few years, so for a short-term investment, that's a better choice. But the savings account grows exponentially, so it will eventually be worth more than the government bond and will continue to go that way. So if you put these in Desmos, take a minute and stop and practice putting these both into Desmos, looking at how they grow and when this one is going to overcome this one. The next part is to go ahead and use your graphing technology to graph the two investment options and show how the money grows in each. So I'm going to start with the initial amount of 1,000. It's going to be plus 20 times x. And see, I need to adjust this because we start off, we're going to start at 0, and I'll go to 20. I'm not sure how far I have to go out, so I'll just do that. With the y-axis, I'm going to start at 0. We're not going to go into the negative. That doesn't make sense, at least not right now. But I'm going to start with, we start with 1,000, so let's go up to 10,000. Okay, let's see if I can see more of my graph. There we go. So you can see it's going to increase by $20 each year. Now let's put that second equation in. Okay, we're going to start with 980 because we had to subtract that $20 to set this account up. Okay, and we're going to add 2%, so 1 plus 2% raised to the power of x. All right, now I can see that if you adjust your graph, that they're going to both start off the same. Let me zoom in a little bit. This linear equation is going to start off quicker because 980 is down here, but they soon meet, and then this exponent, they meet right here, okay, at 11.354, and then it's going to continue to increase exponentially. So I can slide this up, or I can click on a point. Okay, and it's going to continue to overtake that first equation after several years. All right, so practice using your graphing technology. See how it grows. Activity number 2 on page 304. What do you notice and what do you wonder? So just write down something that you notice, something that you wonder. It could be anything. You could notice that these are two different functions. We've called one f, function f, and one function g. With function f, we're multiplying 2 times our input. Our input is x. To get our answer, whatever x is, we multiply by 2. For g of x, we're going to take 1 and 100 and raise it to the x power. Is 1 linear, do you think? Is 1 exponential? Well, I can see this is exponential, and this would be linear. Y equal mx plus b. When there's no b, b is 0. All right, use these two functions, graph them, put them in Desmos, complete the table of values for functions f and g. So pause right now and put this expression in, 2 times 1. Maybe you can do this in your head without a calculator. 2 times 10, 2 times 50, 2 times 100, and 2 times 500. And put your answers here. 2 times 1 is 2, 2 times 10 is 20, 2 times 50 is 100, 2 times 100 is 200, and 2 times 500 is 1,000. Now we're going to take 1 and 1/100th and raise it to the first power. So that's just going to give us 1.01. Now we're going to raise it to the second power, or square it, and it's about 1.10. So round off I usually round off to the nearest hundredth. And then we're going to take 1.01 to the 50th power. So put 50 here for x, about 1.645, and keep going with replacing this with 100 and 500. You could also put this function in and then just follow along on the x-axis. So let me show you how to do that. All right, so we can put the function notation in. G of x is equal to 1.01 raised to the x power. So let's just look at this one. (1.01) raised to the x power. I think I'm going too far up on the y-axis, so let me change that. Go from 0 to 10, so I can see that a little bit better. All right, there's 1.01. Slide up to 0. There we go. Now we're going to move up to 20. So 1 would be 1.01. Keep going up to 10. 10 would be about 1.11 if you round it to the nearest hundredth, or 1.105. 20 is 1.22. I forget what we're going here. 50, 100, and 500. So 50 would be 30, 40, 50 would be right here. (1.65) approximately. You can write out to the nearest thousandth if you want. And then keep going over to 100. And so forth. All right, lesson debrief. We have two linear functions. For example, f of x equals 1/2 x plus 100, and g of x equals 2 times x. How can we tell which one grows more quickly? Will the one that started out with the lower initial value catch up with the function that starts out with the higher initial value? Not necessarily, so really rely on Desmos to graph it, especially if you're not used to looking at just the formula, and then compare. What do they start out with? This one starts out at 100. This one starts out with 0. Okay? And then which one's going to grow more quickly? We're taking x and we're doubling it here. We're halving it here, but we're starting out higher. What about these? Initial amount is 100. We're growing because this number is greater than 1. But put these into Desmos and see what happens. This growth factor is bigger than this growth factor because 2 is greater than 1 1/2. Even though we start out with a smaller amount, this should overtake this graph. This is a linear equation. Y equals mx plus b. So we start at 1,000. And then we're increasing by 300 each time increment. This one is exponential, so even though it starts out very small, it should overtake this one. Go through the summary and glossary. Make sure you're highlighting important information and you're reading this to try to get a better understanding of your functions. All right, complete the cool down for this lesson. I believe this is lesson 18. We have a function here. you should recognize that this is a linear function. Y equal mx plus b. So the starting location is 3, and the rate of change is 10, or the slope is 10. But now we have a function g given by g of x equals 2 to the x. Which function reaches 50 first? Now you could make a table, start with 0, 1, 2, 3, 4, 5, or you could graph it. Graphing it's much quicker, but you can see that when you get to 5 in both of these functions, okay, f of 5, 10 times 5 is 50, plus 3 is 53, and g of 5, 2 to the 5th power, is going to be 32. So function f reaches 50 when x is 5 before g of x, the exponential function, reaches 50. Which function reaches 100 first? So you can plug in values, you can graph it. Graphing is easier for me. And you can see that when we are at f of 7, we're only at 73. Replace x with 7. 7 times 10 is 70, plus 3 is 73. And then g of 7, or 2 to the 7th power, is 128. So g is starting to catch up, and it's going to increase much quicker when we get to 7. All right, here's your practice, page 297, 1, 2, 5, and 7. Complete these in your workbook. Ask questions. Make sure you're not just getting an answer, but you're answering the question. Page 307, 1, 2, 3, 4, 5, and 6. Again, answer the question completely. You'll be given 2 opportunities to do this with a build after the first time that you've turned it in. But don't wait too long. You have until the end of the week to get this done. We're taking our test on Wednesday, so everything is going to shut down as far as turning in work for Unit 6 next Wednesday. All right, good luck. Take your time. I know you can do this. Do the best you can. Ask questions. I'm here to help.